for organizing and summarizing data. So in this chapter, we're basically going to be concerned with several different characteristics of data. The shape of your data, the center of your data, variation, outliers, and time. So the shape of your data. So the shape of your data is, well, is the data all bunched up next to each other, or is it spread all out? So in this chapter, we're going to be looking at this question graphically. So is the distribution what's called bell-shaped? Is it uniform, or is it, well, what's called skewed? We'll be looking at histograms, bar graphs, pictographs, polygons, and curves. We will consider what's called the ogive and density scale histograms. In density scale histograms, the area will correspond to the percentage frequency in each interval. So the density is the percentage frequency divided by the class width. Next, will be, so after we sort of look at the shape of our data, we want to know, where's the center of the data? Give me a representative value that indicates where the center of the data is located. These will be numerical measures. These will be called measures of central tendency. Next, we'll be looking at the variation. We want to somehow measure the amount that the data varies. This will be done numerically. These are going to be called measures of dispersion. Next, we want to look at outliers. And the reason we want to consider outliers is because they could greatly affect our drawings and the way that we organize our data. And so we have to consider outliers. So outliers are values that lie far away from the vast majority of the other values. We will also consider how things change over time. So, suppose we happen to have, say, I collect 10,000 pieces of data, and I write them all on a piece of paper, and I tell you, well, what does the data look like? And your eyes go glossy, and you're like, well, I don't know, that's a lot of data. It's hard to sort of see what's going on by looking at a lot of numbers. So there may be ways to organize the data so that it is easier to visualize. So suppose that we have, what did I say, 10,000 different pieces of data, but they only take on 20 differing values. Well, in that case, I could organize it according to a frequency distribution. So when working with large data sets, it is often helpful to organize and summarize data by constructing a table called a frequency distribution. So you can use both a calculator and computer software to generate frequency distributions. And so let's look at a frequency distribution. We'll also be looking at what are called group frequency distributions. A frequency distribution lists the value of the random variable along with their corresponding frequencies. the corresponding counts. So a frequency distribution is a set of ordered pairs, X, where X represents the value of the random variable, F, where F represents the corresponding frequency or corresponding count of those values of the random variable. A group frequency distribution lists the data by grouping them in intervals. And so a group frequency distribution is a set of ordered pairs where we first do our class interval, which is an interval of values that the random variable can attain. And F is the corresponding frequency. So let's first look at frequency distributions. Then we'll look at group frequency distributions. So let me do an example. Given the following set of raw data, organize the data as a frequency distribution. So I have here the following set of raw data: 2, 3, 3, 4, 4, 5, 5, 5, 5, 6. So first thing to do is, well, let's try to organize this as a frequency distribution. So let's see, let's put X and F here. So let's see what values the random variable can take. And so my random variable can take on the values 2, 3, 4, 5, and 6. So I'll just list here 2, 3, 4, 5, 6. Next. Let's see how many 2s there are. Well, there's 1, 2, 2 3s, 2 4s, 4 5s, and 1 6. So that is my frequency distribution. 1 2, 2 3s, 2 4s, 4 5s, and 1 6. Okay, so let's do that in Excel. So let's go to Excel. Oh, first here, wait. Let me grab, I'll just grab all these guys here. Now let's go to Excel. So I'll put them all here. And then, oh, oops. I didn't need an X there. Okay, so here are all my data values. Maybe I want to send to them. Okay, so there they are. So now let's construct a frequency distribution. So X, F. So it can take on the values 2, 3, 4, 5, 6. Okay, good. And let me make it look nicer. Okay, so let me count all of these guys in here. Now, let's count all of these. have a value of whatever's here. That's in C10. Oops. C10. Okay, now, if I tried to drag this down, well, notice as I'll get error. So what I should do here is let's highlight this and give it a name. Let's go over here and call it, I don't know, X. So now, let's call this X. So now it will do it correctly. So now it'll only change the value of the C10. And just make that 11, 12, 13. And that's what I want. So 1, 2, 2 3s, 2 4s, 4 5s, and 1 6. Good, just like what we had from before. Okay, so and this just explains how to do that. And also, I guess, I think I put that somewhere. You can grab that file. So, a fair disk, a fair die, has been rolled 40 times, and outcomes have been recorded in the following table, actually. Let me copy that. Organize the data as a frequency distribution. So let's do this. Let me go and let's put it, oops. How did that get so much bigger? Somehow it expanded. Let's go, I don't care where I put the data. Let's put the data here. Okay. And let's just semi-copy that for a second. So I'm lazy. Okay, so it has a 1 in here. So there's a 1. Let's make this all a nice color. Okay, so it goes 1 through 6. So let's call this X instead. Oops. Let's redefine. Let's go up to function name. There it is. So let me define this X by something different, by this. Okay. So now let's do count. Yeah. Let's call this X. Good, highlighted it. And let's put a 1 there. Okay. Pull it down. So there are 6 1s, 2 2s, 7 3s, 9 4s, 7 5s, and 9 6s. Let me do it by hand. That's enough. Yeah, there, I can finally see it. Okay, so the differing values the random variable can take are 1, 2, 3, 4, 5, and 6. there are 1, 2, 3, 4, 5, 6 ones. One, 2 twos. 1, 2, 3, 4, 5, 6, 7 threes. 1, 2, 3, 4, 5, 6, 7, 8, 9 fours. There are 1, 2, 3, 4, 5, 6, 7 fives. There are 1, 2, 3, 4, 5, 6, 7, 8, 9 sixes, which is the same thing I got if I use Excel. So a frequency table is useful if I have at most 25 differing data values that I can attain. But what if there are more than 25 data values that I can attain? Suppose I have 1 million pieces of data, and they can take on any one of 100,000 differing values. Then doing a frequency distribution doesn't help. That's you still have like 100,000 numbers to look at. So that doesn't help. So we will look at a group frequency distribution. So a group frequency distribution. So when the range of the data is large, the data must be grouped into classes that are more than 1 unit in width. And so, in general, you should use a group frequency distribution with a number of differing values that the random variable can attain is greater than 25. So you should use a frequency distribution when the number of differing values that the random number can attain is between 5 and 25. And at least one value of the random variable is repeated. So that's when you should use a frequency distribution. So let me look at a grouped frequency distribution. So a group frequency distribution has, well, your class interval denoted by X and your corresponding frequency. So this says that there are 5 numbers between 10 and 20, 3 between 20 and 30, 2 between 30 and 40, 3 between 40 and 50, 2 between 50 and 60, 3 between 60 and 70. So let me look at this a little bit more closely. So the lower class limit is the lowest, smallest number in the class interval. So if the class interval is, let's say, 20 to 30, then the lower class limit is 20. The upper class limit is the largest number in the class interval. And so in particular, in this particular example, the upper class limit is 30. So the basic rule of thumb is that the class limits should have the same decimal place value as your data. Now, you could write these intervals in two different fashions. So one way of writing them is this way. The exclusive type classes, or I could do it as an inclusive type class. And so I could write it as 50 to 69, 70 to 89, etc. And so I could write it in that fashion. So your lower class limit is the lowest number in your class interval. Upper class limit, largest number in your class interval. The lower class boundary is the upper class limit of the preceding class plus the lower class limit divided by 2. So let's look at the interval 50 to 59 to 69 and 70 to 89. So this, notice that there's a gap here. It says 69 here and 70 here. So the upper, well, let's do the lower class boundary for this boundary is 59 plus 70 divided by 2, which is 69.5. So the lower class boundary for this second interval is 69.5. In general, your class boundaries will end with a 5 and have one more place value than your data. So the midpoint between 89 and 90 is 89.5. So your upper class boundary for this class is 89.5. So let's say the lower class boundary for the class interval 70 to 89 was 69.5. The upper class boundary for the class interval 70 to 89 was 89.5. So the basic rule of thumb is that the class boundary will have one additional place value of the data as the data, and it will end with a 5. The class marks, sometimes also called the class midpoints, are the lower class limit plus the upper class limit divided by 2. So I have here the interval 10 to 20. So the lower class limit is 10. The upper class limit is 25. Therefore, the class mark is 15. So the lower class limit is 50. The upper class limit is 69. 50 plus 69, 119 divided by 2 is 59.5. So the class midpoint for the class 50 to 69 is 59.5. Okay. The class width is the lower class boundary minus the previous lower class boundary. And so the class width here, 30 minus 20 is 10. So the class width is 10. And so the class width here is, well, let's see. 20 minus 50 is 70 minus 20. 70 minus 50 is 20. Now, in general, so the class width is again the lower class boundary minus the previous lower class boundary. If you're talking about these classes where they join up, my exclusive type classes, then define the class width. It doesn't really matter what you do. You can subtract class midpoints. You can subtract the class boundaries, or class boundaries this way, or this way. Or in this case, you could do it also with the class boundaries. So all of them come out with the same number. That's not true for inclusive type classes. Okay. If at all possible, you should try to make every class width the same. So in this case, you look at all the class widths, they're all equal to 10. So I say that this frequency distribution has equal class widths. But sometimes it's not possible. So sometimes you have your data, and maybe, it looks like this, but then there's maybe another piece of data that is maybe 10,000. So you have all this, and then one piece is way, way out there with the 10,000. And so you should then go, well, 70, 80, 80, 90, etc., till you go all the way to whatever is at 10,000 or whatever. Or what you could do is use what's called an open-ended frequency distribution. You would just say 60 or above. You would say below 20. So you could open up one or both of your limits here at these class intervals, at these boundaries, at the upper end or at the lower end, to grab a hold of a particular outlier. So open-ended group frequency distribution, either the lowest class interval has no lower class limit, or the upper class interval has no upper class limit. And so if you have outliers, sometimes you will need to use open-ended frequency distributions. So there are two different ways to write these intervals. One is an exclusive type class. The other is as an inclusive type class. So the exclusive type classes, these are exclusive type classes, are such that the class limits are the same as the class boundaries. And so if you look here, there's no gap between the 20s. And so in this case, we have, well, a little bit of a problem, because what do you do with the 20? So the question is, well, if you have 20, which one does it go into? Does it go into this first one or into the second one? Well, suppose you had, the interval 90 to 100 or 85 to 100 was an A, and 70 to 85 was a B. Well, where would you put the 85. Would you say you got an A or a B? Where everyone goes, oh, you got an A. So meaning you would put it here rather than here. And that's what we do. So the class 10 to 20 will mean I include 10, but I do not include the 20. So you include those that are the lower class limits, but you don't include data equal to the upper class limits. Except, for the one exception, if I had the data 70, I would include it in here. So except for this very last one, you wouldn't need to write 70 to 80, just include that one piece of data at exactly 70. So it turns out that the mathematics is easier for exclusive type classes. So usually they're used in the physical sciences. So, and again, this is because the mathematics is easiest for these. I will be using during lecture in the lectures. So I'll be doing that in the lectures. The inclusive type classes, these 50 to 69, 70 to 89, 90 to 109. So these are inclusive type classes. In inclusive type classes, the class limits are not the same as the class boundaries. And so, for example, the class 10 to 19 means, well, you go from the lower class boundary to upper class boundary. It means that X is between 9.5 and 19.5, the lower class boundary and the upper class boundary. It includes 9.5, but it does not include 19.5. So these are usually used in the social sciences. The mathematics is more difficult. So the basic rule of thumb, as you recall, is that the class limits should have the same place decimal value as the data, and the class boundaries have one additional place value, and this additional place value will have the value 5. Okay, so let's look at some examples of inclusive type group frequency distributions. So IQ scores on low lead group inclusive type classes. So the lower class limits here are 50, 70, 90, 110, 130. The upper class limits 69, 89, 109, 129, 149. The lower class boundary for this first class is 49.5. The upper class boundary, 69.5. For the second class, the lower class boundary is 69.5. And the upper class boundary, 89.5. For the third class, lower class boundary, 89.5. Upper class boundary, 109.5. For the second to last class, lower class boundary, 109.5. Upper class boundary, 129.5. For the last class interval, the lower class boundary, 129.5. Upper class boundary, 149.5. The class midpoint, found by adding the upper and lower class limits, 50 plus 69 divided by 2, 59.5. 70 plus 89, 159 divided by 2, 79.5, and you get 89.8, 99.5, 119.5, 149.5. The class width found by subtracting the lower class boundaries. So 69.5 minus 49.5, 20. Actually, I did. Yeah, that's how we define it. 89.5 minus 69.5, 20. 109.5 minus 1 minus 89.5, 20. 129.5 minus 109.5, 20. 149.5 minus 129.5, 20. So now, how do you make a good frequency distribution? So you should have between 5 and 25 classes. So K here, usually we denote the number of classes by the letter K. So K should be between 5 and 25. If you have less than 5, well then, you really can't tell what's happening to the data because there's not enough numbers. If I group everything in one category, well, that doesn't tell me a lot. And certainly you shouldn't have more than 25. Then that's just too many numbers to look at, too many things to look at. You should use exclusive type classes if possible. The classes should be mutually exclusive, continuous, and exhaustive. And they should have equal class width. So there is no one technique that you can use that's applicable for all data. But there is a simple way of trying to at least satisfy some of these above stated properties. Even though I say they should have equal class width, it could be that some of your data is bundled closely together and then spread out. In which case, for the things that they're bundled closely together, you should actually have more classes in that area. And then where it's spread out, then make those classes have bigger class widths. But I'm hoping that the data doesn't look too weird. If the data doesn't look too weird, then you use equal class widths. So that's if the data allows us to do that. So some rule that gives us some of these properties is the Sturgis Rule. So it doesn't really use any facts about the data. Since it doesn't use any facts about the data, it won't be applicable in those cases where the data is sort of bunched up in places and spread out further apart in other places. So if the data is relatively uniformly distributed, then Sturgis Rule isn't bad. Then it's somewhat applicable for most situations that you'll be looking at. So for most situations you will be using in most of your classes, this will actually give you a good starting point. So Sturgis Rule says that K, the number of classes, is equal to 1 plus log n, where n is the sample size, divided by log 2. So the idea for this rule is as follows. So first, if you have only one piece of data, then you should only have one class. So when the sample size is 1, then the number k of samples is 1. Then every time you double the sample size, you should add one more class. And that's what this is. So if you have one data, if n is 1, then k is 1. Every time n doubles, you add one more to k. So now, let me try to do this. And so let me try to figure out what this is. And let's actually do it on some data. So let's try to see if I can do this on some data, and we'll come up with some complications, in which case we will then need to proceed with some sort of algorithm to help us proceed. So let me look at example 4. Suppose I have the following set of raw data: 10, 11, 14, 15, 16, 20, 22, 28, 31, 35, 45, 48, 50, 55, 56, 68, 69, 71, 71, 73. So I have all that data. So now I want to use Sturgis Rule. So here's Sturgis Rule: k equal 1 plus log n over log 2. So let's figure this out. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 numbers. So I have 20 numbers. So let me get out my calculator. Everyone should get out their calculator now. So get out your calculator and let's plug this in. And so I want 1 plus log 20 divided by log 2. So what did people get? Not all at once. So it is, you're calculating 1 plus log n, which is 20, divided by log 2. Oh, I see someone got it. Someone 2 point, okay, 2.82. 2.82. So far we have agreement on 2.82. Okay, anyone else? 2.82. Oh, okay, we have agreement on that so far. Okay, so what I get, however, is 5.32. So I bet you what you're doing. Let's see. I bet you you're doing this. 1 plus log. Let's see how you got this. 20 divided by. I bet you this is what you did. Log 2. Ah, that's the error. Parentheses error. Okay, so no, that's wrong. It should be 5. So do it again. So do it again. So what you notice here, you should end your parentheses. So let me clear that. So you should write in 1 plus log 20 in your parentheses, divide log 2, and then hit enter. And that'll give you your right answer. Did anyone not get that answer? 5.32. Oh, I guess some people, let's see. Oh, got it. Okay. So, okay. Some people are saying, yeah, got it now. Got it now. Okay, good. Um, what I will say is that the usual student error when doing calculations is parentheses. So it's almost always, yeah, it's almost always an error in parentheses. So if you get a number different than what I get, check your parentheses. So if someone's saying, oh, I didn't realize you had to close the parentheses. Yes, this is why I have you do it yourself. Because you look at me doing it and it's hard to see that I closed. It's hard to see those little parentheses, etc., that I do. So unless you do it yourself, you go, I was supposed to close the parentheses there. Then you notice. Okay, good. So 5.32. So now let's go back. And so I have, so that's how many classes I want. So let's say I had numbers that went from 0 to 50. And I had k equal 10. And so the classes were 10. Actually, the number of classes were 10. Then what would be the class width? Well, let's see. If I had 50 numbers that went from 0 to 50, so they're a range of 50, and I wanted to put them into 10 classes, what should my, and suppose I have equal class widths, what should my class width be? What do you think? So I have 0 to 50, and I want to do 10 classes of what size? You should do 0 to 5, 5 to 10, 10 to 50. Okay, let me do it a little, let's do it a little smaller. Suppose you had number 0 to 20, and you had 2 classes. What should be your class width? If you want to split it into 2 classes, what should your class be? Yeah, 10. Okay. And how did you figure that out? You said, oh, well, I took 20, divided it by 2, and got 10. Okay. So let's do the same thing here. I have here a 5.32, k equals 5.32, etc. And that's the number of classes. So I want to figure out what is their class width. Well, let's take what our range of numbers is. Well, I go from 10 to 73, and then divide that by k, and that should give me the class width. And so I'll take the range of data, just like what I did before, 20, divided by how many classes there were, 2, to get out to 10. And so let's go back to my calculator. On the TI-83, it's easy to do something like this. So I'm going to do parentheses. My maximum number here is 73. I'll subtract from it the minimum number, which is 10. Let me in my parentheses, divided by this number here. I'm going to be lazy, and I'll just say it was my previous answer. So I get 11.83781,496. Did everyone get that? You may or may not, depending on your calculator, you may or may not have a previous answer. Most calculators allow you to do the previous answer. Some don't, where you need to either store your answer somewhere or rewrite it again. So many calculators have a place where you can store previous results. and many have it where you can retrieve previous results. Okay, so now let's go back and then see all the problems we're now presented with. So now, oh, so there. So now I'm looking here. So this says that my class width should be 11.8 something, but my data are whole numbers. So the place value for my data are the ones place value. But the class width should be the same as your data values. So the class width should have the same value, whatever, maybe I didn't say it. It should have the same, it should be to the same place value as your data. And this obviously is not to the same place value. So you're gonna have to figure out something from there. Next, the number of classes is a number. You count the number of classes. Number of classes can never be anything except for an integer. You can only have 3 classes, 12 classes, 0 number of classes, but you can't have 5.32 number of classes, right? Because you're counting how many classes you have. So K can't be 5.32. So let's think about it for a second. Which is easier, having an additional class or making the class width bigger or smaller? Well, changing the class width really doesn't affect what we do, but having an additional class is a little bit more work. So I should first try to minimize the number of classes, if at all possible. So that will be the idea going on here. So now, let me go through these steps. Hopefully with that example, at least the start of that example, we can now go through this semi-algorithm. So here, when doing homeworks and tests, do we round our answers or do we enter the whole number, the whole answer? So it would depend. So it would depend on the question. Some questions ask you to round. If they ask you to round, then you would round to the digit they tell you. If they don't tell you to round, then you would input the whole number that you see on your calculator. And so that's what you would do. In your particular classes, after this class, they will tell you an algorithm on how they would want you to round or whatnot. Usually, for most times, their algorithms are actually incorrect, but they'll pick an arbitrary algorithm, usually an incorrect algorithm that actually is very prone to error. Okay, so oh, so the answer is no, not yet. So someone's saying, what do we do with K? That's what I'm going to explain now. So that's what my explanation will be. So let's go over the algorithm. So constructing a group frequency distribution. So first, determine the number of classes K. So don't do any rounding or anything yet. K equals 1 plus log n over log 2. So that's what we first did. 2, calculate the class width, range over K. Again, no rounding or anything else. Now, if K is an integer, or well, actually a whole number, and if H has the same significant digits as the data, And if the minimum value of your data plus h times k is greater than or equal to the maximum, then you proceed to the end. So then you just draw your group frequency distribution. So what it says is that if we're lucky enough that this number was 5, and this number here, so if we're lucky enough that this number is an integer, and if we were lucky enough that this number were, let's say, some class width equaling something that has the same place value as our data. In this case, the same place value is the ones place value. So let's say that this was an 11. Then we will be done if, given that number of classes in this class width, we're able to fit all the data in that particular grouping. So let's see what that says. So suppose we were that lucky that we said, oh, we want 5 classes, 1, 2, 3, 4, 5 classes of class width 11. Let's see what this would mean. Well, you start at, well, where do you start? You start at the smallest value. So the smallest value here is 10. Where do you want to end? You want to end so that I can get the number 73 in this last class. If I can't, I'm in trouble. So you want that that all the numbers here are going to be able to be put into one of these classes. So let's see. Let's look at this number here. So let's start at 10. And let's look at this. Well, that number here is just 10 plus 11, the 21. Now let's look at this number here. Okay, so now let's look at, so I start at 10, I add 11 to it to get 21. Now, how do I go from 21? Well, at 21, I'm going to have to add 11 to get 32. That's 21. But 21 was 10 plus 11. I'm adding another 11. So that's really 2 times. So now let's figure out this. Well, I'm going from 32 to, well, let's add another 11. 32 plus 11 is 43. So I'm going from 32 to 43. Let's figure out how I got to 43. Well, it was the previous 32, which was 10 plus 2 times 11. And I added to it an additional 11. So that's 3 11s. Well, let's do the next one. I can probably guess it. It's 10 plus 4 times 11. 44 plus 10 is 54. Yeah, that's right. 10 plus 5 times 11. Let's see, 55 plus 10 is 65. Yeah, that's correct. But now I have here, the class widths are all 11. Yes. There are 5 classes. 1, 2, 3, 4, 5 classes, yes. But it ends at 65. I can't include any of those numbers in this frequency distribution. So therefore, it doesn't work. But if this last number here were bigger than, greater than or equal to 73, then I would be able to include it. So if the minimum number, 10, plus h times k, whatever 5 times 11. If that were bigger than the maximum number, 73, then I would be done. I could then draw my frequency distribution. I would start at my starting point. I would choose the minimum number as the smallest number in my group frequency distribution. I would then use the whatever h and k I got from this above algorithm. I explained the above algorithm and tally up everything. So I would figure out what h and k are and put everything into each of these classes. So remember, my viewpoint was that I should minimize the number of classes. So first, I will truncate k. I will then use that truncated k and see if when I truncate h, if it works, or when I round up. Well, let's see, maybe I should use h rounded up. So round up. Round up h. Two significant digits. Obviously, it's okay. I had my fingers located in the wrong space. Okay, so so first thing is you round down h. So I take h rounded down. So it'll be 11. I truncate k, 5. And so I then check, can I put all these numbers into this situation? So the smallest number was 10, k was 5, h was 11. 5 times 11 is 55, plus 10 is 65. So no, it won't include all those things, anything bigger than 65. So no, this doesn't work. So now the next step is, well, round up. And so I'll round this up. And so instead of a round down, I'm going to do a round up to the significant digit. And so I'm going to round this to 12. So I'll round this up to 12. And let's keep the same k. Remember that adding classes is harder. So I'll increase the width. And so let's see if this works. So k is 5, so 5 and h is 12. 5 times 12 is 60, plus my minimum number, which was 10, is obtain a frequency distribution for a set of raw data. And so let's do that. So what we did here is we had some raw data and we determined the number of classes by using the following formula. K is equal to 1 plus log of n. There are 20 numbers here. So log of 20 divided by 2. We got 5.321928095. We then determine the size of the classes, H, to be, well, the range of the data, 73 minus 10, divided by the number of classes, which is that 5.3219289095, to get 11.83781496. Since neither of these are, well, the number of classes has to be a integer value. Actually, it has to be a whole number value. Well, it could a whole number value. Then the H here must have the same number decimal place value as the data. And so the significant place value here was a ones place value. So this has to be the ones place value. So to do that, we said, well, okay, first let's see. Let's first round down both the, so I'll truncate both the K and the H. So I truncate K, so that it becomes a whole number. I'll truncate H, so that it becomes, well, I truncate it to the units, to the ones place value. And so I get here, K is 5 and H is 11. But then you take the smallest value in my set, 10, plus K, 5 plus 8 times H, 11. Not 5 times 11 is 55, plus 10 is 65, which is not greater than or equal to the 73. So we then added 1 to the place value of the K, of the H. And so I got 12. And so now we check. 10 plus 5 times 12, 60, plus 10 is 70, which again is not greater than 73. We have to keep going. Now we take K, add 1 to it to get 6. Keep our original truncated value of H. And so we get K, 6 times H, 11, 66, plus 10 gave us 76, which indeed was greater than or equal to 73. So this works. Therefore, we should have 6 classes of size 11. And so we start with our lowest data value, 10, plus 11, 21, plus 11, 32, plus 11, 43, plus 11, 54, plus 11, 65, plus 11, 76. And that gives us 1, 2, 3, 4, 5, 6 classes of class width 11. I then, maybe I'll grab this for a second. Try to determine my frequencies. So between 10 and 21, there are 2, 4, 6 numbers. Between 21 and 32, there are 3 numbers. Between 32 and 43, that's just 1 number. Between 43 and 54, there are 3 numbers. Between 54 and 65, there are 2 numbers. And between 65 and 76, there are 5 numbers. Therefore, my frequency distribution my group frequency distribution looks like this. So 6 numbers between 10 and 21, 3 between 21 and 32, 1 between 32 and 43, 3 between 43 and 54, 2 between 54 and 65, and 5 between 65 and 76. Any questions about that? Oh, do we have a test today? No, you do not have a test today. We need to finish off chapter 3. We only got to, we finished chapter 1 and we started the beginning of chapter 2. So the exam will probably be next week, not this week. Okay, so in later chapters, you'll be looking at things that are important, distributions that are important, such as the normal distribution. So one key characteristic of a normal distribution is that it is bell-shaped. So the frequencies will start low, and then they'll increase to a high value, and then they will decrease to a low frequency. The distribution will be approximately, will be symmetric, with frequencies preceding, with the fact that the upper half is a mirror image of the lower half. Let's talk about gaps. The presence of gaps can show that we have data from 2 or more different populations. However, the converse is not true, because data from different populations do not necessarily result in gaps. Let me do the following example. The table below is a frequency distribution of randomly selected pennies. Discuss what the distribution of the weighted pennies might tell us. So let's look at this. So here I have some pennies. So I have 18 that weigh between 2.4 and 2.5 grams, 19 between 2.5 and 2.6 grams, 0 between 2627, 2728, 2829, 2 between 2.9 and 3.0, 25 between 3.0 and 3.1, 8 between 3.1 and 3.2. Would anyone guess why would a sample of pennies have a distribution that looks like this? So why would it look something like this? So your distribution goes like this, and then like this. So why would a distribution of pennies look like that? Any guesses? Anyone? Why would a distribution of pennies look like that?
It's because of the type of the material of the penny.
Yes, because pennies have evolved over time. So the presence of gaps can suggest that the data are from 2 or more different populations, in this case, 2. The weights of pennies in grams are presented. The examination of the frequencies suggests 2 different populations. So usually it was said you had a copper penny. It's no longer copper. So it's really not a copper penny anymore. Matter of fact, if you flip a penny now and you listen to it when it hits the ground, it doesn't have the same sound as older pennies. So pennies made before 1983 were a copper penny, 95% copper, 5% zinc. Pennies made after 1983 are only 2.5% copper and 97.5% zinc. So if you actually look at a penny, so take a penny and you turn it sideways, you'll see that it's not, that what they've done is just a very you know, the front and back sides have a very, very microscopically thin layer of copper. Everything else is not copper, it's zinc. And so it's no longer a copper penny, it's a zinc penny. And so, and the reason for that was the cost of copper was too high. As a matter of fact, currently the copper, and zinc are too high. So there have been discussions that they will stop the production of pennies because, well, pennies I think currently cost somewhere around 2.5 cents per coin to you know, in both printing cost and you know, the cost of the actual material. So they actually cost much more than what their quote unquote value is. And the fact that I think like 98, somewhere between 98 and 99% of all pennies are out of circulation. So they keep making pennies and they just disappear from circulation. Because what happens is people get pennies and they don't give them back. They just sort of put them away, throw them away, or whatever they do. But they don't actually give back pennies to be put back in circulation. They usually, you know, when you buy something, they'll give you a few pennies, but then you never give back those pennies. They just get lost. They're out of circulation. So, reasons for constructing frequency distributions. Large data sets can be summarized. So we can analyze the nature of the data. We have a basis for constructing important graphs to organize the data in a meaningful and intelligible way, to enable the reader to determine the nature or shape of the distribution, to facilitate computational procedures for measures of average and spread, the measures of central tendency, and the measures of dispersion, to enable the researcher to draw charts and graphs for the presentation of data, to enable the reader to make comparisons